Hi, everyone. Welcome to Foresight's Molecular Machines Group. I'm really delighted today to have Ben Roberts here with us today. And you will be discussing an engine without a machine, which is, I think, a topic that has, in various different philosophical forms, really inspired and confused humanity for a long time. And you have a new take on it. And I will be in the chat monitoring for questions. I'm going to share a lot more about your bio and your work in the chat. But for now, I think we're just really excited to hear from you. Thank you so much for coming on, and the stage is yours.
Okay, so the topic really of my talk today is going to be about first the process of designing molecular machines. This is really some of my PhD work. And then I'll move on from that and talk about the lessons we learned in the kind of the mechanism that lies behind these molecular machines, the information ratchet, and move on to what I've really been doing as part of my postdoctoral work at the University of Padua, applying these mechanisms outside of the context of molecular machines to look at kind of some of the opportunities that we get from this non-equilibrium behavior. So I'll start off by pointing out that I've not done this by any means on my own. So first, Leigh and then Prins, who've been my supervisors for my PhD and postdoc respectively. And then a special shout out to Stefan, who's been there basically for all the molecular machines related things. And then the people whose names are in bold are the people who are involved in working in these two pieces of work directly, and other people, other collaborators through the years. Start off with really, I want to consider what I mean by an engine in just a broader context, really, than molecular machines to start off with. What I'm thinking of when I talk about engines, and people are welcome to disagree with me, but for the sake of this talk, it's helpful to have a framework, is this black box that I have on my screen, which is something which you can put in some kind of fuel, take out some kind of waste, and the black box will mediate that process in order to transduce some of the energy released to perform something like movement, for example, is probably the most familiar one. But also it could be something like responding to the environment, or it could be replication. Movement is most familiar on the macroscopic scale, where our fuel might be petrol or coal. But also I would lump that into the same category, for example, a lithium ion gradient in a lithium ion battery. So this really is not fuel as maybe we're used to thinking about it, but anything where there's a potential energy gradient. And the motor, the engine, will transfuse energy from the process where fuel is converted into waste in order to perform its task. For the time being, I'm going to lump all of the tasks into their kind of category of active behavior. Because really in this talk, what I'm more interested in to start with is the way in which this black box works. How does it take energy from the fuel to waste process and convert it into doing something interesting? There are several problems that are faced, especially when trying to convert ideas from the macroscopic scale down to the molecular scale. And I'm just going to run through a few of them. So first of all, we can't really do anything that involves a heat gradient. The scale is so small, the distances are tiny, and so there's no way of maintaining a meaningful heat gradient between over those distances. And what this means is that we can't use strategies that you might use in traditional engines, for example. So techniques used in coal, steam engines, or petrol engines are completely out. They're not open to us at this scale. The next is that there's no meaningful momentum at this scale, which means if we want something to be moving, you have to be applying a force to it continuously. As soon as the force stops being applied to it, then the movement will stop in that direction. Or more precisely, it won't stop, but it will become random. That's because the Brownian motion, which dominates. And this really is because the scale of the motors or the molecules we're working with is not that much bigger, or can even be smaller than the solvent molecules. And so just the thermal motion on the solvent molecules will cause completely random motion in our machine. And at the face of it, this might seem like it's killer for the concept of a molecular motor, because all of these concepts are completely vital the way in which a macroscopic engine or a macroscopic motor will work. You couldn't do a petrol engine without heat gradient or without momentum, or where things were dominated by Brownian motion. But really, this is not just a challenge, it's actually an opportunity as well for us, because we can start to use these features to build a new type of motor. So for example, instead of an heat gradient, which is hard on this scale, we can access a chemical potential gradient. So this is where we have some higher energy fuel, whether it's a molecule or whether it's a concentration gradient, and through catalyzing the process by which that is converted to waste, our engine can harness some of that energy to do active behavior. The fact that we have no momentum is quite good in some ways, because it means that the motor can make mistakes. It doesn't always have to be perfect and go forward all of the time. Sometimes it can hop backwards and then the error can be fixed later. And you can think about how problematic this might be on a macroscopic scale if suddenly your car, from going at 70 miles an hour on the motorway, decides for a second that it's going to go backwards 70 miles an hour instead. That might be catastrophic on a car, but for molecular motor, not a problem. And so this really gives us a little bit of tolerance that we might not otherwise have. And the way to take advantage of that is using something called a dynamic kinetic resolution, which means that we can use probabilities and pick through rates in reaction which direction the motor is going to turn in. Finally, the fact that Brownian motion dominates means that we can just approach having movement in a different way compared to what we might do at the macroscopic scale. So instead of worrying about causing the movement, instead we can expend our energy in terms of stopping movement going in the wrong direction. And really combining these three elements hopefully gives you something that will act reasonably as a molecular motor if you can do it properly. And so this really is what we've tried to do in my PhD. So in my PhD, we designed this molecule. It's a biaryl molecule. It forms atriopisomers, which is where the top ring can only face one face of the bottom ring, and it can't rotate. If you want a motor, obviously you want it to be able to rotate, and so we can remove that blocking group, and now it can rotate through half of the rotation is available, switching between the two forms. In order to do the second part, you need to form an anhydride, you need to form a tether by reaction with a carbodiamide, and now that can exchange through a ring flip mechanism on the other side. And then to return to our initial acid form, you can take an anhydride hydrolysis catalyst and break the tether. And so that completes the rotation. But it doesn't explain where the directionality comes from. We use chiral reagents that can react with one form of motor more quickly than the other. So the chiral fuel reacts from one side, and then the chiral anhydride hydrolysis catalyst reacts from the other. And so by performing these reactions in a cycle, where you're always forming, or you try to form the anhydride from one side and hydrolyze it from the other side, in the process of doing the chemical reaction, you converting fuel to waste, you perform continuous rotations. That's quite a lot to look at in a video, only about a minute and a half. So to break those steps down, the motor accesses the chemical potential from the fuel to waste reaction, the carbodiamide to add plus water to urea reaction, by being a catalyst for that process. So we take our acid, react it with the carbodiamide, that forms the urea and the anhydride form of the motor, and then the original acid form of the motor is regenerated by reaction with water that's just in the surroundings. That is a spontaneous process, the formation of urea, and so you get a directional chemical reaction cycle from this, and that allows us to use some of the energy released by the spontaneous chemical reaction in order to do directional rotation. Briefly, we know that it's happening because we can follow it using NMR. So we can add the reagents stepwise. So DIC is our carbodiamide in this case. So we add carbodiamide to our acid. You can see the shift of the peak there to form the anhydride. And then once we add in water and the catalyst, we see a return to the carboxylate form, the acid form. But you can't really extrapolate stepwise operation that well to autonomous operation, where everything's happening at once. We need to also do this autonomously, and you can see basically the same thing is happening. This time when we add carbodiamide, our DIC, you see the acid peak decreases a little bit, and you see an anhydride peak appearing. And then once the fuel has run out over here, then all of the anhydride goes away and we just see acid again. And so we know that our motor is mediating this process. We know it's performing the catalysis, and it is therefore able to harness the free energy released by the fuel to waste process in order to do directional rotation. But this doesn't tell us whether or not it's actually doing directional rotation, just that it's opening and closing. In order to know whether it's doing directional rotation, you've got to look at another part of the process, and this is the dynamic kinetic resolution state that we get. This really is just an observation that species 1 and species 4, the two different H isomers, the acid, the aqueous form of the motor, can exchange by rotation, and they can exchange pretty quickly by rotation. Then they can both react with the carbodiamide to form urea and the anhydride. But because of the chirality of the carbodiamide fuel, you're more likely to react species 1 to get anhydride 2, so on the left-hand side, this bit, compared to reacting acid 4 to get anhydride 3, this on the right-hand side. Likewise, the two anhydrides can actually exchange rapidly as well, and this time using the anhydride hydrolysis catalyst, anhydride 3 reacts more quickly than anhydride 2. So we're more likely to regenerate the acid form of the motor as species 4. Putting the whole thing together, because everything is all happening in the solution together, is what gives us our Brownian ratchet mechanism, our information ratchet mechanism. Because somehow species 1, it seems to know that it should react faster than species 4, and likewise species 3 seems to know that it should react faster to species than species 2, and that is related to the idea of having information about how it should behave. What you can see is, hopefully, is that there's an outside pathway around this cycle and an inside pathway around this cycle. The outside pathway goes around in the clockwise direction, and the inside pathway goes around in the anti-clockwise direction. And because of the dynamic kinetic resolution steps, the outside pathway that goes from 1 to 2 to 3 to 4 and then back to 1 is faster than going in the opposite direction. And this kinetic asymmetry is really the driving force behind an information matching mechanism that makes this motor turn. The other way of seeing it is by looking at the Curtin-Hammett diagram for the processes. We can break them up into two. Firstly, we have our acid forms that can exchange rapidly, so go from 4 to 1 plus fuel. And then they can react to form the anhydride, but because the energy barrier up here is low for 1 to 2, we react preferentially in that direction. And then drawing the second energy profile, 2 and 3 can also exchange rapidly. So we go from 2 to 3, and then once again hop over the lower energy barrier as controlled by the chiral hydrolysis catalyst to return to 4, which puts us back on our original surface. And so really what we're doing is completing the cycle by always going at the easier pathway, by going over the lower transition state energy barriers, which is just like following the ratchet in our corner, moving in the anti-clockwise direction and not allowing it so easily to move in the clockwise direction. Unfortunately, that's the opposite around. One of the nice things about using external sources of chirality to control direction is that we can explore where the direction comes from. So we can use a completely achiral system. So we can use DMAP, which is an achiral catalyst, and DIC, which is an achiral fuel, and in combination. So no external chirality provided, we get no directionality observed, as it should be. If it wasn't like this, we'd worry. Then using one chiral fuel, the S chiral fuel, we can drive the motor in one direction to the left, and using the R chiral fuel, we can drive it to the right. Then similarly with the chiral fuel, the chiral catalyst drives to the left and right. So with the chiral fuel, we can also drive it to the right with the R and NT1. And then we can start to create matches or mismatches. So if we mismatch the fuel here and the catalyst here, we decrease the directionality that we observe slightly. Whereas if we create a matched pair, then we increase the directionality slightly. And then we can really start to play with it, because knowing combinations of fuels and catalysts that we can use, we can basically drive the motor back and forward in different directions as we choose. So using the chiral fuel, we can initially drive the motor in one direction. And then once the chiral fuels run out, we can use the achiral fuel and a little bit of the catalyst to drive it in the other direction. We can then increase the concentration of catalyst, but use the other enantiomer and push it back in the first direction. And finally, use loads of the opposite enantiomer of the catalyst again and drive it back in the second direction. And really, so long as if we could wash out the catalyst from this, we could just drive this motor backward and forward as long as we liked, to be honest. So this is really the design for a molecular motor. The aim is getting directional rotation, and we've seen that you can use H isomers that on their own can't rotate, and thermodynamically couldn't rotate directionally even if they could perform full rotations. And then by applying some kind of fuel, we can get them to go perform unidirectional rotation, or at least directly biased rotation. But something that's worth noting is that bond rotation isn't a special chemical reaction. It's just a reversible chemical reaction. So you can easily wonder, okay, if we can influence the direction of bond rotation using this method, can we use a similar kind of information ratchet mechanism to take any chemical equilibrium reaction that's from a reversible reaction and start to disequilibrate it, move it away from equilibrium? So could we, for example, take these two DNA duplexes, which are exchanging and in equilibrium, and using an information ratchet mechanism where we provide fuel, drive them so that we increase the concentration of the RT duplex at the expense of the GT duplex? So here, to look through the design of these a little bit more carefully, you'll notice that I've drawn a colored strand on the top, which forms a duplex with the black template strand on the bottom. The colored strands are colored this way because they have fluorophores bound to them. So the red strand has a red fluorophore, and the green strand has a green fluorophore. And both of these also have quenchers at the opposite end of the strand. So when a DNA strand is not part of a duplex, it's floppy, and so the fluorophore ends up being quite close to the quencher, which means the fluorescent signal is quenched. And when it forms a duplex, this is much more stiff, and so the fluorophore is held further away from the quencher, and therefore we get a signal. And so by following the fluorescent signals in this system, we can deduce the concentrations of the different components. You may notice that the template strand has these overhanging bits here. These are called toe holds, and this is a very normal mechanism in DNA nanotechnology. But for anyone who's not familiar, this is we take advantage of something called a toe hold mediated strand displacement reaction. And that's where, because the red strand and the green strand bind on different sides of the template, the green strand can bind on the 3-bid, the toe hold, and then slowly unzip the red strand until it falls off. And so you get exchange that happens much more quickly than would be possible if you had to completely rip the duplex apart and then rebind. And this also allows us to not worry too much about having 3 template in the reaction, which would complicate things quite significantly. So in order to get this to do anything, we have to add something else, another reagent, which we've termed a fuel strand. And the fuel strand is, in this case, just another single strand of DNA, which is complementary this time to the full length template. And therefore, because it's complementary to the full length, it binds more strongly than either R or G. And so it displaces them in general. But adding this just sets up a three-way equilibrium. There's no dissipation of energy in this system yet, and so the cycle cannot be directional. And so we need another step. And the way we provide energy dissipation in this system is to use an enzyme called uracil DNA glycosylase, which takes uracil residues and just hydrolyzes them off the DNA backbone to make an A-basic site. And this is a spontaneous chemical reaction. It releases free energy and allows us to drive things in a set direction. The trick here is that there are uracil residues on the fuel strand, so that by using this enzyme, we can convert the fuel strand to a waste strand. And there are 3 uracil residues on the side where R binds, and only 1 on the side where G can bind. And what that means is that the red R strand can displace the waste strand far more rapidly than the green G strand can displace waste. And so overall, what this does is it means that we install a kinetic asymmetry where we're able to drive RT to GT to FT to WT and then back to RT in preference of going in the opposite direction. This is basically the same thing as happens with our molecular motor diagram, but you'll notice that the actual simplified reaction diagrams, as I'm showing here, are quite different shapes. So on the left, this is the typical diagram that you might see from a molecular motor, where the arrows indicate particularly strongly directional steps where we might consider energy dissipation to be happening. In this case, even though they look different, they are actually very similar because they include all of the same important features for an information match mechanism. So they include 2 sets of gatings, one which is just the ratio of rates of 2 similar reactions. They both include an energy dissipation step, although interestingly, the DNA network only has 1 dissipation step for all cycles. And they include a ratcheted or driven process. There's only 1 for the DNA, which is driving between the red and the green, whereas there can be 2 for the motor. But again, this is just a semantic difference, if you like. What some of you might have noticed is that I've only been talking about 2 cycles so far, and that is cycles which are both dissipative, they convert fuel to waste, and they involve the ratcheted step, which is in this case from red to green or vice versa. So the 2 cycles I've considered so far are the red to green to dark blue to light blue. So red to green to fuel to waste and back to red. That would be the forward cycle that we want, whereas there's also a backward cycle, which is green to red to fuel to waste back to green. And really the essence of our problem is that most of all, we want to make the forward cycle occur faster than the backward cycle. But I would be wrong to ignore all of the other cycles that are possible in this network. So first of all, because of microscopic reversibility, technically we can read those cycles in reverse. This is really unlikely because it involves converting waste to fuel, which is an energetically unfavorable reaction, but we should acknowledge that these are technically possible cycles. What we can't really ignore is the futile cycles, and futile cycles are cycles where you get conversion of fuel to waste without interconversion of red and green. So we can have a green futile cycle or a red futile cycle. And again, technically speaking, we can do those in the opposite direction. And finally, we have slip cycles where no fuel is converted to waste or vice versa, but we still get some conversion between the red and the green strands. And these are important because they don't involve energy dissipation, which means that they can't be directionally biased. You can't follow this cycle in one direction more than the other, and therefore they're inherently non-directional, which is a bad thing if you want to have a non-equilibrium process. So the tricky thing about these information ratchets and these non-equilibrium cycles is that you're really trying to only make this one forward cycle happen at the expense of all other possible cycles within the network. And understanding whether your system is doing that is a really quite complex task. And you really have to break down the process to looking at each step as carefully as possible. Luckily, with the DNA system, that's actually not so hard, and we can do a lot of steps, follow a lot of steps kind of one by one, building up our understanding of the network as we go. First of all, we can take our RT duplex or our GT duplex and add the dual strand to them and see what happens. And what we notice is that we go from a concentration of 1, effectively normalized, and we decrease the concentration to a new equilibrium position as the fuel strand displaces the red strand or the green strand. It's hard to see here, but the green strand is actually displaced marginally faster than the red strand. What's not so hard to see is that once we add the enzyme, the UDG, the red strand recovers, the RT duplex recovers in concentration much more rapidly than the green duplex. The GT duplex recovers in concentration. And this is because, as I was saying before, the uracil residues on fuel, and therefore the abasic sites on the waste, are much more on the side of the red strand. So the red strand can bind much more quickly. The next thing we can do, once you understand the kinetics of these processes, is to try and do it all together. So with both the red duplex and the green duplex, RT and GT, and do the same set of reactions. And you'll notice that basically the first step behaves pretty similarly. Both the red and the green duplexes are decreased in concentration as red and green strands are displaced by the fuel strand. And then the red strand behaves pretty similarly after the UDG is added as well, as it quickly displaces the waste and recovers back to its nearly original concentration. The big difference here is that the green strand recovers, or the GT duplex recovers in concentration much more quickly as well. And what this shows is that there's a new pathway that's been opened up for forming the GT duplex. So instead of directly displacing the waste strand with the green strand, instead, we should first displace the waste strand with the red, and then displace the red strand with the green. And so what this shows is that directional cycle that we've been interested in is in fact taking place, where we can follow green to GT to FT to WT to RT and then to GT. By understanding the kinetics of this system, we can actually start to build proper kinetic models that describe the whole thing and fit them to the data. And rather pleasingly, when we build it, as I've described and shown here, the data it fits really rather well to the model's predictions. And this again indicates that we are understanding pretty well what's happening in these systems as they react. But doing it again, like with the motor, doing this stepwise is only really half the story. We want to be able to do everything all at once to get an autonomous operation where you're getting continuous cycling around this network. And so to do that, we need to do a different set of reactions or add them in a different order. So basically, we need to start with the enzyme present before we even add the fuel. And so as soon as we add the fuel, the cycle is kicked in. So we want to follow a certain set of steps that we should see. So first, we take the red and the green strands in solution, and we add a template strand to them. And because duplex formation is fast, what we expect is that the initial concentration of these two duplexes should be pretty even, randomly distributed. Then we should let those react until they are equilibrated. And once they're equilibrated, we know that the red strand binds slightly more strongly, so we expect to see slightly more the red strand, the red duplex and the green duplex. Then when we add fuel, we expect to start to form some kind of kinetic selection on this, where we're going to deplete the green duplex, displace the green strand, and replace and form the red duplex again from waste. And so what we expect to see is that as we follow this sort of cycle I've drawn out once, linear here, but as a cycle, when we go red, RT to GT to FT to WT, RT, back to GT, back to FT, and continue doing this cycle of reactions. we expect to see an increase in the concentration of the red duplex. What do we see? And does our kinetic model work for it? Yes. In effect, yes, it does work. As soon as we add a template strand, both of the duplexes are formed in pretty much even concentrations. Then we allow them to equilibrate, and there's more red than green. Then once we add fuel strand, we get an immediate displacement of the two colored strands, followed by, as the enzyme kicks in and starts to convert fuel into waste, a pretty fast recovery of the red strand and a slightly slower recovery of the green duplex. One thing that's really interesting to note here is that the concentration of the RT duplex actually goes above what we'd expect at equilibrium, and this really is indicative that we're seeing this kind of non-equilibrium cycle taking place, because there's no way this can happen through just allowing a concentration to equilibrate. And effectively, I guess if you want, you can think of it like you've got two buckets, one representing GT and one representing RT, and you're taking water out of the GT bucket, putting it into the RT bucket, and that's allowing the level of water in the RT bucket to get higher than the GT bucket, even though maybe it can flow between them. The difference is even more stark when you look at the ratios. You can see that at the initial point, we're sitting at about 1-to-1. Then when we get to equilibrium, they're nearly 2-to-1 in favor of the RT duplex. But once we add the fuel, the ratio jumps up, and so we have a much higher bias in favor of the RT duplex. This is even more pronounced when we use a higher concentration of fuel, although it starts to get a little difficult because the concentration of the RT and GT duplexes gets very low. But nonetheless, we see a very high bias towards RT in the kind of non-equilibrium phase of the reaction before all of the fuel is consumed and the species return towards equilibrium. One thing that would be really nice to do is to try and operate the system continuously, effectively using a chemostat. So this is where the concentrations of the fuel and the waste remain constant, and we just see how the system responds to those changes. Currently, this is not experimentally possible, but we can do that with our kinetic simulation fairly easily. And so what happens when we supply fuel at a constant rate to this system is that we see a very similar behavior where initially the concentrations drop, and then the concentration of the RT duplex climbs above the equilibrium concentration and then sits there, effectively having reached a steady state, while the concentration of the GT duplex just drops and stays low. We can also simulate what happens when we turn the flow of fuel off, in this case, and you can see that there's an initial jump in the concentration of the RT duplex as all of the remaining FT duplexes are converted into waste and then displaced. The waste is then displaced by the red strand, causing this bump up here. But overall, the species then relax back towards their equilibrium values. This is interesting to look at in terms of the ratios, because as we're supplying fuel, we climb up from the equilibrium ratio up to a steady state ratio that's high and not dissimilar from the ones that we observed experimentally. Then as soon as the fuel is turned off, the ratio starts to decrease, and until it eventually reaches equilibrium again. Something that's interesting and maybe a bit new in terms of the analysis that we've tried is a different approach to viewing the duplexes. So one thing we can do is imagine that our red duplex is a 1 and our green duplex represents a 0. And then we can start to look at the entropy or the entropic potential, to make the numbers positive, viewed along the axis of just the ratio between changing RT to GT. So this is the entropy associated with just the degree of freedom involved in the exchange that we're interested in, the driven process. What we can see is that, again, as you'd expect from an entropic calculation, the entropy, the amount of energy you have to put in to sustain the kind of the highest ratio is higher, and then as it gets closer to just 1-to-1, that's a more entropically favorable situation. Taking this curve is interesting because if we look at this on a single measurement level, so single measurement of the identity of a single duplex, we can actually relate this to the idea of information. And then using this logic, we can apply that to the ratios that we measured. And we see, as expected, that when in our random case, we have zero information because we have no idea which color we're going to pick if we pick out a duplex. Once we've reached equilibrium, there's a little bit of information that we have already because there's a slight bias. So we know that we're slightly more likely to pick out the red duplex. And then once we are in the driven situation where we're converting fuel to waste, then our amount of information is drastically increased because we can make a fairly good guess that the duplex that we're going to pick out is most likely to be the red one. This is a direction that is interesting in research because there's something known as the eigenparadox, which many of you may be familiar with. But briefly, it's the idea that in order to sustain life, we need to error correct things like DNA replication. And the error correction basically requires very complex machinery in order to do it. But the problem is, if you're using complex machinery, how do you build the complex machine without error correction? And so you end up in a chicken and egg sort of situation where how can you have your error correcting machine without error correction? And how can you do error correction without your error correcting machine? And what we think this is starting to show is that really all error correction actually needs is some kind of information ratchet mechanism that doesn't necessarily need a particularly complicated machine. And sure, the error correction from a generic information ratchet like this might not be particularly good, but with such simple structures, it doesn't necessarily have to be. And so this is really, hopefully, an interesting avenue for future research, just to know whether an information ratchet might explain how you can do error checking in order to make very simple self-replicating systems become complex enough to be considered alive. So we can hopefully take our idea of the chemical engine and divorce it from the concept of the machine. Thank you, everyone, for listening. And if anyone has any questions, I'll be happy to answer.
Wonderful. Thank you so much. I will try to perhaps put my video on in a second and just see how it goes, because your Wi-Fi was actually quite good. So we could try it out. It's nicer for the Q&A, but that was amazing. Thank you so much. Really appreciate it. And you have a ton of questions already in the chat. I don't know if you saw it, but we'll start from the top. And so I will ask, the first one we had Steve Folks, then we have Jeremy Barton, then we have Dean Estumian, etc. So I will just be going down the list until we run out of time, which might be soon, because there was a lot of fantastic discussion in the chat. So that's really encouraging. Yeah, Steve Fawkes, if you want to unmute first.
My question was about the use of the word momentum, and based on your initial diagram of the engine with the fuel turning into behavior, I was considering that from a metabolic perspective, and when you said that there was no momentum involved, I didn't take that as meaning, let's say, atomic momentum, which would be so amazingly trivial. But I think that discussion went through in the chat just fine, and that metabolic momentum isn't really the right way to refer to it. Question is, if you want to comment on it, that's fine, but I think the question resolved itself.
Yeah, nice. Okay, yeah. I was meaning specifically to say the physical momentum, or I think Dean Weiss's comment, really inertia is the correct thing to say. So I'll jump straight and say, yeah, Dean's correct. It's inertia that I was referring to specifically here.
The question that I would like you to answer is, have you considered how your mechanism might lead to an actual epigenetic switch?
Once you get real biological mechanisms involved in things, the complexity just goes through the roof. And so it's very hard. But yeah, for sure, you can imagine genetic switches being based on this mechanism, because ultimately what this is about is performing some kind of kinetic selectivity. So all you would need is some way of accessing a set of DNA or something more rapidly than another set, or the inverse logic of slowing down the rate at which you can access some part of DNA. I wouldn't be massively shocked to find out that's exactly how some genetic switches in biology work. So, yeah.
I was specifically thinking about hydration, that there's a thermal dehydration mechanism that you talked about briefly. And that when you're talking about a newly fertilized cell, you're talking about 90% hydration. And when you're talking about childhood development, it's down to maybe 55%. And in adults, 45%, that changing hydration levels could have a huge effect on a mechanism that's driven by hydration.
Yeah, very well. It could do, yeah. And you can imagine the chemistry of that working out. But again, like I said, the complexity of these things gets huge. And we're really at the very start understanding kind of chemical reaction networks in the level of detail that's needed to really engage with questions like that. You can see I've got 4 different species on my diagram. I've done one paper where I had, I think, 12, and it was so difficult to learn things from that system. So eventually, that's the hope. Eventually, we'll get to the level where we can start to engage with these questions.
Thank you.
Wonderful. We have, because the discussion went all in the chat, so I'm just going to check if any of your points, or if technically in the queue I have Jeremy, Dean, Ted, and then Stefan. Jeremy, do you still want to ask your questions, or do you think it's been handled in the chat?
A little bit in the chat, but I'd like to discuss more at some later date. Very cool.
Perfect, thank you.
Awesome. Yeah, agree. Dean, is your question still relevant?
No, I think that that was answered. It is inertia, the tendency to continue moving rather than momentum, which is a conserved quantity and not something that we can play with.
Yeah,
Awesome.
right.
Then, yeah, thank you. Then I guess we have Ted and Stefan, and I think those are relevant.
Oh, hi, Ben. I'm Tad Hogue. Thanks for this really interesting talk. So my question is, when you have these engines that are operating in solution, I was curious, what is it in practice, the limiting step? Is it how long it takes the fuel molecules to diffuse to the engine and start the reaction? Or is it they get there quick enough, but then the reaction takes a long time?
Yeah, this is a really good question. With the motors that we are working with right now, and this makes things easier for us as well. At the moment, it's the rate of reaction with the chemical fuel that is the rate limiting step. There's certain requirements that it has to be. We have some examples where the rate of rotation, the physical rate constant, for example, bond rotation might be the rate limiting step, and that is really problematic when it comes to making working motors. There's a pretty strict requirement that for the most effective motor, or the most effective non-equilibrium system in general, you want specifically using an information matching mechanism, which, sorry, it's a thing I'm mainly adding for Dean and manually. But using this mechanism, you want the rotation to be fast relative to the chemical steps, and the chemical steps really have to be the rate limiting parts. What biology does so well is it makes its chemical steps really fast as well, and then just eats everything faster and faster. But currently, yeah, it's currently just the rate of reaction of the chemical fuel that should be our rate limiting.
Okay, thank you.
Wonderful. Stefan, you had a few questions.
Hi, Ben. Yeah, great talk. And obviously, I'm quite familiar with this work from having chatted to you before. But a question I don't think I've asked you before, is it possible to coarse-grain biological proofreading DNA down to a binary process to make it analogous to what you're doing here? And if so, is it possible to get a meaningful comparison on efficiency?
Possibly.
What I'm really asking is, how far behind are we on proofreading? Or 7 orders of magnitude behind biology?
Yeah, 7 orders is not a bad guess. Probably biological proofreading gives you roughly a 7 orders of magnitude advantage. Takes you from about 10 to the 3, one mistake in 10 to in 1,000 to one mistake in 10 million or something. So that's
in terms of the Ratchet constant, right? But in terms of
basically, yeah, not done the maths properly, but yeah. Biological proofreading is a bit more complicated because it's not just a binary process; it's a ternary process or whatever.
Yeah.
But Yeah, I think you could potentially do some of the same maths if you were clever enough and worked out the right way, but I'm not there yet myself. I'll need help.
Yeah, you and Emmanuel, you can tell me the answer to that in a few years' time. Maybe.
Yeah.
Lovely. Thanks a lot.
Okay, wonderful. Let me know if I'm forgetting anyone here in the chat. I definitely don't want to step over anyone, but I feel like lots of the discussion afterwards was, again, chat discussion. So please just raise your hand if you still have a question, by all means. I have a few more general questions that usually people would like to answer to. So one of them, for example, is if you could just extrapolate forward. I know that you've gave him like some kind of like an outlook already for the next few years, but what's like on your docket for the next year or for the next few months? How are you concretely trying to push this research forward? And then the next question after that, let me just ask this one first.
So from my perspective, I think that one of the kind of two challenges really I'd like to talk about, which are what I'm interested in, so that's why I'm mentioning them. The first is a theoretical challenge. So as was mentioned earlier, we are still working with the simplest version of these systems that we can make, because that's all we can really deal with mathematically as well as synthetically. It would be amazing if we can begin to push our understanding beyond that to use complex multi-cyclic systems and understand how various chemical and physical quantities move through such networks. And this kind of theoretical thing will be really interesting, especially if we can keep showing the experimental evidence that goes along with it. And that really has to be lockstep theory and experiment. So I think that would be a really interesting challenge for the next few years, maybe. Another one is, I think we have to start really finding useful stuff with this. Molecular motors it's hard to find a really useful application for them. But as I've indicated, motors are just one potential thing that these information ratchets can do. I want to really start looking for non-equilibrium advantage, where we can really start using the control of the kinetics that we've now worked out how to do in order to do jobs better than you can really do them at equilibrium using current technology. And that's what I'm interested in finding in the future, in the next few years, hopefully. I have some ideas, but not concrete ones yet.
Yeah, what do you think is holding back most progress on the path to applications? I really love that you're just putting your finger on that. It's definitely something that we keep coming back to. Any specific things that you think are just like blocking this right now?
The main thing is that even at this level of like this simplicity, they are horrifically complicated. The number of things that can go wrong and do go wrong regularly when we're trying to design them. I've been working on these now for more than I care to think, 7 years. And I still feel like every single time we look at a new motor or look at a new system, there's something else that's broken about it that we have to fix. And the kind of understanding things like understanding that your rate of rotation has to be fast relative to your chemical steps. It was there in the first design, but we didn't realize how bad it was if you slowed down the rate of rotation until it happens. And then it kills everything and you have to redesign everything back up. So the level of understanding is currently what's really holding this back, because it's so hard to learn to design. But hopefully in the future, we'll become, once we've made more concrete sets of rules, we'll get there. We'll get there.
It's an exciting time too. I guess you're always discovering something else that's broken.
Yeah.
Okay, wonderful. And then if people in this group are excited about like the research that you've already produced, which I think they really were quite excited about it, but then also looking ahead, what can people like listening to this talk right now in this seminar room, but then also people afterwards finding it on YouTube or something, how can they help you work along? If you could venture out a few requests, now is a great time to do so.
Good. It's how can people help? It really is a case of, I think I'm going to stick with more or less what I said in the past. It's people it literally is people engaging with the ideas and learning from our mistakes. If they can read our papers and start to understand where we've gone wrong, and then just trying out and designing their own systems. And we're starting to see this. So we're starting to see more people writing papers which are talking explicitly about information ratchets, or talking explicitly about non-equilibrium. There's a particularly nice paper from Emanuele Hussein and Massimiliano Esposito in 2019, which has a very simple equation for calculating the sort of free energy difference between a given state and its equilibrium. People using things like that and knowing things, and people like, again, Dean Estumian's work, people engaging with Dean Estumian's work and reading what 20, maybe 30 years ago about the opportunity these things give, and maybe revisiting those ideas, just engaging with this subject more and understanding what they're actually trying to do, rather than just seeing something that kind of looks cool and then just stopping there. And that would be amazing if people did that. That would help a lot.
I'm hoping that we can contribute a small amount to that by getting people excited about that work, this talk. Thank you so much for me, and I think I'm echoing Ted Kayla as well. It was a really understandable presentation. I'm not technical in that field whatsoever, and nevertheless, I think I have more of a handle now of like how these things might work. So thanks a lot. It was a really well done presentation. Thanks everyone for listening, for your great questions, for the exciting chat discussions, and I'll see you again for the next one here.